All right, in this next video, we're going to look at the properties of acids and bases. But let's start out first with acids, and we'll make just a simple list of some properties associated with it. Okay, so the first one is what we've covered already, and that is that acids produce hydronium ions, which is H3O plus, in water, right? So if you mix an acid in water, you'll always get H3O plus. The next one is a little bit funny. It's that most acids taste sour, right? I normally don't recommend tasting any sort of reagent in lab, but if you're at home, citric acid, which is found in citrus fruits, tastes kind of sour. So if you bite into a lemon, that's that sour taste that you're sensing. All right. The other thing is you can test acids and bases with litmus paper. So if we had an in-person lab, we could see this, but it turns litmus paper red. It's a really quick way to determine if some sort of unknown solution is acidic or basic is just to put a drop of the solution on litmus paper. If it turns red, it's acidic. If it turns blue, it's basic. It's really nice. All right, and then the last one is what we're going to spend a little bit of time on. So they often do what are called double displacement reactions. Or sorry, double replacement. All right, and let's take a look at a couple of these. Doesn't do it with all compounds, but it'll do it with a number of them. So with hydroxides or oxides, what you often get out is you get water, right? You get water and you get a salt. Right? And then if we look at some other compounds, like carbonates and bicarbonates, you still get water and a salt, right? We saw this in our previous video. But if you recall, when we did our carbonates lab, we also got CO2 that was kicked out. So the way you can remember this is most acids will produce water and salt, but if you see the word carbon in here, right, there's a good chance you're going to be producing CO2. Essentially, it will decompose. So let's take a look at some examples of this. And I wanted to kind of show you breakdowns of how these works. So let's say we've got magnesium oxide, right? That's a solid. And if we combine this with an acid, I'll just pick an acid, we could have HCl. So HCl is aqueous, meaning it's dissolved in water. And if we were to react this, a double replacement reaction means that each compound is essentially going to do a switch with the other. The way I like to describe this is imagine two partners swing dancing, or two couples swing dancing, and then they exchange partners. That's what's going to go on here. So we're going to get Mg. However, magnesium is 2+, which means it needs two chlorines to bounce out. And this will be aqueous. And then we are going to get water, which is a liquid. So we need to double check that everything's bounced. So we need 2 HCl over here in order to make sure that we've got an equivalent number of atoms on each side. So what this is called is the molecular equation, right? This is what we're pretty familiar with seeing throughout the term. However, we can break this down even further, right? And what we can do is we can show the total ionic equation. And the whole idea with the total ionic equation is you break everything up into ions that can be broken up into ions, right? So let's think about it this way. If we're dealing with magnesium oxide, this isn't broken up into ions in its solid form, right? So it's not existing as free-floating ions. They're bound together in a crystal lattice. So we're going to leave this as is. However, anything that's in water and can dissociate, we're going to break apart. So you see how over here, this is in water? That means we need to break this apart. So we're going to break up. And if we do that, we're going to get 2 equivalents of protons, and those will be dissolved. We're just going to go with the Arrhenius definition and leave out the H0+. And we're also going to get 2 equivalents of chlorine, specifically chloride. It's got the negative charge, and this will be aqueous as well. So because this is aqueous, we will split it up. In fact, let me do a little arrow thing here, and we'll say these will dissociate in water. All right. Like I said, magnesium oxide over here isn't in water yet, so it's not dissociated, it's just a crystalline solid. All right, so we're almost there. Let's go to the other side. Magnesium chloride over here is in water. We can tell that because it's listed as being aqueous, so same sort of idea. We want to break this up. And in the ionic form, it's going to be Mg2+, and that's aqueous. So we're going to split that up. And we're going to get 2 equivalents of chlorine, or chloride. And that will be aqueous as well. Again, we're going to split this all up into pieces. And water in this case, we're going to just show as being regular water. It's not being broken up or ionized, at least not as shown, so we're going to leave it as this. So this would be the total ionic equation, all right? But let's kind of take a look at this, because there's oftentimes a net ionic equation. And what the net ionic equation does is it excludes any spectator ions, right? So what is a spectator ion? Well, a spectator ion is present on both the starting material side and the product side, right? So let's see if we can find any of these. So if we go over here and we look at magnesium oxide, there's no magnesium oxide over here. So that's not a spectator, right? If we look at H+, there's no H+ over here, so that's not a spectator. It's doing something, all right? But over here, we've got 2 chloride ions, and over here, we've got 2 chloride ions. So what we're going to do is we're just going to kind of cancel these out for that portion. And for the net ionic equation, we're going to ignore it. So that leaves us with magnesium oxide solid left over, plus our 2 equivalents of protons. We're going to skip our spectator and go straight to the product side, where we'd have magnesium 2+ cations that are aqueous plus water. All right, so it is important to remember that the net ionic equation excludes spectator ions. All right, I hope that makes sense. As we can see, this is an oxide, so we're not going to get any CO2. We're just getting our salt and water out. All right, let's take a look at another cool property. Okay, so this was kind of an example for what was above here, but we're not done with this bullet point list. All right, so I'll start this bullet point list up again down here, but the next bullet point is that acids can react with specific metals, or certain metals, I could say, to produce H2 gas, right? Some of you might actually remember this from the water lab, right? In the water lab, you saw a video where we put a magnesium strip and hydrochloric acid. The hydrogen bubbles went up into the test tube, and we were able to light it with a match. Okay, so let's even draw this out as a equation, right? So we started out with magnesium solid plus HCl, which was aqueous. And when we did this, we made hydrogen gas And we have to predict what else. Well, in this case, the only thing left over is going to be magnesium and chlorine, right, from our starting material side. Magnesium is 2+, which means we need 2 chlorines, which are each 1-, in order to bounce that out. And because this was in a water solution, it's going to be aqueous. So this would be our molecular equation. All right, but let's try to break this up into our ionic equation. All right, so same idea, magnesium is solid, so we leave it as is. However, HCl is aqueous, so we're going to break that up into its individual parts, like this, all right? However, H2 is still going to be a gas. It's not dissolved, so we can't break that up. But over here, with magnesium chloride, it's aqueous, so anytime you see aqueous, we break it up into parts. So we'd have a magnesium 2+ ion that's aqueous, plus we would have 2 chloride ions, which are also aqueous. All right, so let's do the same thing we did before. And this time we're going to do the net ionic equation. Okay, which means we need to identify any potential spectator ions. And here's one that students often mess up. They say, well, there's magnesium here and magnesium here. But you notice how it's not the same magnesium? The magnesium on the left is a solid, where on the right it's a cation. Therefore, they're not the same. So we're going to skip that. Then over here, we'd say H+. We have hydrogen over here, but again, it's different, right? And then over here, we've got chloride and chloride, so it does look like that would be our spectator ion. And some of you may have even noticed too, I forgot an important thing. We forgot to bounce our equation up here. So we need to put our 2 here. That way we're not creating or destroying atoms during this process. So now we can see that things are bounced correctly. All right, so let's do our total or net ionic equation. If we ignore our spectator ions that I've highlighted, we'd have magnesium solid plus our 2 protons that are aqueous would go to hydrogen gas plus magnesium 2+, which is aqueous. So it's kind of unique that metals will do this. They dissolve and produce hydrogen gas. But I will say that not all metals do this. Only certain metals will do this. And in fact, the book has a decent list of metals that will do this in a table. So let's go ahead and blow up this table. This is table 9.5 from your textbook. But you can see that there's some metals that simply won't do this. So for example, copper, mercury, silver, platinum, and gold, they don't react with acids. And then other ones, like these, they require really high acid concentrations to react, where other ones will react even with water, which we know can act as an acid. It just depends on the metal. So this isn't a universal truth. It just depends on the metal. But it is a kind of unique phenomenon. So in the example we looked at, we said magnesium, and it does react very slowly with water, but it'll react quite rapidly with acidic solutions like HCl. Okay, so let's continue on and quickly wrap up with bases. Okay, with bases, the first bullet point is going to be really straightforward. They produce hydroxide in water, right? So we know that's the definition of base, all right? And they often taste bitter, all right? And I know it's hard to differentiate bitter and sour sometimes, but oftentimes the bitter taste of plants are due to what are called alkaloids, and those are bases. A good example of this, for those of you that imbibe in a cocktail once in a while, would be a gin and tonic. That tonic water has an alkaloid in it, and that bitter flavor is due to the base. All right, and then these turn litmus paper blue. So if you ever have an unknown solution and you want to know if it's acidic or basic, you can grab yourself some litmus paper and actually dip it in and check. And then last but not least, these obviously will react with acids to make salt and water usually, but sometimes it'll even react to produce CO2. All right, that leads me to my last point, is a neutralization reaction. All right, so a neutralization reaction is very specific. A neutralization reaction is a reaction where an acid and a base react completely to produce water and a salt. And like we said, salt isn't always sodium chloride. It could be any ionic compound. So let's put a note here. So i.e. any ionic compound. But the whole idea is when the neutralization reaction is complete, there's no leftover acid or base, which means that the pH of the solution should be 7, right? So when a neutralization reaction is complete, we should end up with a solution that's pH 7. All right, I hope that helps, but if you have any questions, please let me know.